Hello students, in this video we will discuss some more method to solve non-linear partial differential equation. As we have already discussed Char-Pit method, which is general method to solve first order non-linear partial differential equation in two variable. Here there are some standard equation in which some particular methods can be applied. So let's take one by one these standard forms. First standard form is when given non-linear partial differential equation is in the terms of P and Q only. P and Q only means X, Y and Z terms will be absent here. In that case, when X, Y and Z are absent, the partial derivative of F with respect to X, Y and Z all are equals to 0. We can calculate partial derivative. We have some value of partial derivative with respect to P and Q only, non-zero value. And other than these, partial derivative with respect to X, Y and Z will be 0. Now we will put these value in Char-Pit equation, Char-Pit auxiliary equation, which we already know. When we put the values of derivative in this Char-Pit equation, the first term become dp upon 0 as del f upon del x is equals to 0 and del f upon del z is equals to 0. So first become dp upon 0 and second become also dq upon 0 as del f upon del y equals to 0 and del f upon del z equals to 0, and rest of like this. Now to find an integral we are to choose two fraction to get some relation between p and q, but as denominator is 0, numerator will give a relation between p and q only. So let's take first fraction to find a relation in p and q or in at least one of p and q. So when we take dp upon 0, so it means numerator is equals to 0, dp equals to 0. It gives us p equals to a. A is some arbitrary constant. Now we will put this p is equals to a in given equation, which is function of pq equals to 0. When we put here, we get function of aq equals to 0. It means q can be expressed as in terms of a. Say function of a types, capital F of a. Say this is equals to b, which is also a constant, but it is not arbitrary constant. A is arbitrary constant and b is some function of a. Now to find solution, we will put a p and q in dz, which is dz is equals to p dx plus q dy. When we put here, we get z is equals to ax plus by plus c, where a and c are arbitrary constant and b is some function of a. It means if we are given with some equation which is in terms of p and q only, that is x, y and z terms are absent, its complete solution is always given in the form z is equals to ax plus by plus c, where b is some function of a. Okay, so general procedure to find complete solution is that first we are to check that given equation in terms of p and q only, or if reducible, convert it into in terms of p and q. After that, let's take p is equals to a, q is equals to b, and b we can find the value of b from function of pq equals to 0 from given equation, and c is arbitrary constant. So complete solution is always in the form z is equals to ax plus by plus c. So if given equation in terms of p and q, we can direct write its solution, that is z is equals to ax plus by plus c without any calculation. Now its singular solution, we also can find its singular solution. So let's take phi is complete solution, phi is equals to 0. First we calculate partial derivative of phi with respect to a and putting it equals to 0. Calculate partial derivative of phi with respect to c and putting it equals to 0, as a and c are arbitrary constant. And from these three equations we are to eliminate a and c. From these three equations we are to eliminate a and c and get a relation without a and c, which is singular solution. And here when we calculate del phi upon del a equals to 0, we get minus x minus f dash a y equals to 0. Differentiate it with respect to a partially, it becomes 0. It gives us minus x. it gives f dash a, derivative of a, y equals to 0. Now when we differentiate this equation partially with respect to c, we get del phi upon del c equals to 0 implies minus 1 equals to 0. Now here if we get minus 1 equals to 0, which is an absurd result, when we differentiate it with respect to c, it gives 0, second term also becomes 0, third also becomes 0, and fourth gives us minus 1. It means minus 1 equals to 0 from this equation, but this is not true. This is an absurd result. It means in that case, if given equation in terms of p and q, singular solution will not exist. Now we solve some problem. We have p square plus q square equals to m square. Here m is constant, it's given. So given equation in terms of p and q only, as x, y and z are absent. So this is of standard form 1 type. So we will assume p is equals to a and q is equals to b, where b is function of a, which we can find from here. F of pq is equals to 0. So taking p is equals to a, putting p equals to a in given equation, which is p square plus q square minus m square equals to 0. From here we get q square is equals to m square minus a square. So q equals to square root m square minus a square. Now put these value p and q in dz, we get z is equals to ax plus by plus c, as we have discussed earlier, where b is what? Root of m square minus a square. So it becomes z is equals to ax plus root of m square minus a square y plus c. This is complete solution. Here a and c are arbitrary constant. Now let's take another problem. We have z square p square y plus 6z x y p plus 2z q x square plus 4x square y. Given equation contains x, y, z, p and q. All terms, all variables or all parameters are exist here. So if it is possible to convert given equation in terms of p and q only, we can apply this particular method. Otherwise we cannot apply. So first we try to convert given equation into this standard form. To convert it into this form, first we look if there exist any terms without p and q. Here 4x square y exists, here no p and q exist. So divide this whole equation with x square y. Divide whole equation with by x square y. We get, and same time also write p as del z upon del x and q as del z upon del y. So it becomes z square y upon x square y. So z square upon x square del z upon del x whole square. Here we can rewrite it as z del z upon x del x, taking numerator along and denominator along. So z del z upon x del x whole square plus 6 z del z upon x del x plus 2 z del z upon y del y plus 4 equals to 0. Now to convert it into p and q only, we are to use some transformation, and to find that particular transformation we will assume to convert it into p and q, here should be del z and here should be del x. It becomes p. Here should be del z and here should be del y. It becomes q. So let's take z del z as d of z. Z dz is equals to d of capital Z. This is another variable. When we integrate, we get z square by 2 is equals to capital Z. Z we already have, and this capital Z we assume. So we will use this transformation to convert z into some another z. Same, let's take x del x is equals to d of capital X. So we get x square by 2 is equals to capital X. So this is another transformation which convert x into some capital X. And from here let's take y del y is equals to d of capital Y. Y dy is equals to d of capital Y. it gives us y square y2 is equals to capital Y. When we use such transformation, given equation convert into del z x del z. In place of x del z we get del of capital Z upon del of capital X. Here del of capital Z upon del of capital X. In third term del of capital Z upon del of capital Y. So here it becomes capital P, capital P, capital Q. So P square plus 6P plus 2Q plus 4 equals to 0. Now this is equation of standard form 1. We can find its solution using this particular method. So let's take P is equals to A. Here P is capital P. Capital P is equals to A. Putting this P is equals to A here, we will get the value of Q. So we get A square plus 6A plus 2Q plus 4 equals to 0. When we simplify it, we get Q is equals to minus half 4 plus A square plus 6A. Let's say this is B. This is equals to B. So its complete solution will be Z is equals to AX plus BY plus C. In terms of capital XYZ. Z is equals to AX plus BY plus C, where B is minus half 4 plus A square plus 6A. A and C are arbitrary constant. Now putting the value of B, we get this, and when we simplify it and convert capital XYZ into small xyz using transformation, we have Z square by 2 in original variable xyz. Z square by 2 is equals to A x square by 2 minus 4 plus A square plus 6A y square by 4, as 2 is already here in denominator, and from transformation capital Y is equals to small y square by 2, so y square by 4 plus C, or Z square is equals to AX square minus 2 plus 3A plus A square by 2 y square plus C dash, where C dash is 2C. Here A and C dash is arbitrary constant. So now let's take another problem. X square P square plus Y square Q square is equals to Z. It is also in terms of X, Y, Z, P and Q. So we convert it into P and Q only. So very first we write as x square del Z upon del X whole square plus Y square del Z upon del Y whole square minus Z is equals to 0. Now divide whole equation with Z. So it becomes x square by Z del Z upon del X whole square, y square by Z del Z upon del Y whole square minus 1. Now take numerator and take denominator along. We get x del Z in numerator, and in denominator we get root Z del X. In second term we have in numerator y del Z upon root Z del Y. So first we take del Z upon root Z. Wherever Z exists, it exists in same form. So we can use some transformation which replace del Z upon root Z with some dz. So let's take dz upon root Z is equals to d of capital Z. So its numerator become dz, and same times let's take x del x upon x. Del x upon x is equals to d of x. Similarly dy upon y is equals to dy. So when we use such transformation, we get capital X is equals to log x, capital Y is equals to log y, and capital Z is equals to 2 root Z. When we integrate it, we get this transformation. Using this transformation, this equation 1 becomes P square plus Q square minus 1, where P is del Z upon del X and capital Q is del Z upon del Y in terms of capital X, Y, Z variable. minus 1 equals to 0. Now this equation 2 is in its standard form. PQ, function of PQ is equals to 0. No x, y, z present here. So let's take P is equals to A, Q is equals to B, and B will be 1 minus A square. So Q is equals to square root 1 minus A square, and its solution will be given by AX plus BY plus C. So putting the value of B, root 1 minus A square, and finally replace capital XYZ with small xyz using transformation, we get 2 root Z is equals to A. Capital X is log X plus root 1 minus A square log Y plus log C dash, taking this arbitrary constant C in terms of log. So let's say C is equals to log C dash, or using property of log we can rewrite it as log of x raised to power a, y raised to power root 1 minus a square and c dash, and in left hand part 2 root z. Shifting log into left hand part we get exponential 2 root z is equals to c dash x raised to power a, y raised to power root 1 minus a square. So in this way we find complete solution of given problem. A and c dash are arbitrary constant here. Now let's take one more example. PQ is equals to x raised to power m, y raised to power n, z raised to power 2l. First we rewrite it into del z upon del x, del z upon del y is equals to x raised to power m, y raised to power n, z raised to power 2l. So divide whole equation with x raised to power m, y raised to power n, and z raised to power 2l. So it becomes 1 upon x raised to power m, 1 upon z raised to power l, together with del z upon del x, and 1 upon y raised to power n, 1 upon z raised to power l, together with del z upon del y. We can rewrite it as z raised to power minus l upon x raised to power m, del z upon del x, z raised to power minus l del z upon y raised to power n del y, minus 1 equals to 0. So this is first term. Let's take second term, second factor. So first factor, second factor. So from here to convert it into P and Q, let's take z raised to power minus l del z is equals to d of capital Z, x raised to power m del x, x raised to power m del x as d of capital X. Similarly, y raised to power n dy is equals to d of capital Y. When we integrate it, we get the transformation capital Z is equals to z raised to power minus l plus 1 upon l plus 1. Capital X is equals to x raised to power m plus 1 upon small m plus 1. And capital Y is equals to y raised to power n plus 1 upon n plus 1. So using this transformation, this equation 1 becomes del z upon del x into del z upon del y equals to 1, or PQ is equals to 1. Here P and Q are capital P and Q. So let's take P is equals to A, then we get Q is equals to 1 upon A, and its solution will be given by Z is equals to AX plus BY plus C. So it becomes Z is equals to AX plus 1 by AY plus C, and putting the value of x by z we get this a complete solution. We have one more example. Now this is a little bit different type of problem. We have y minus x qy minus px plus is equals to p minus q whole square. Of course this is not in terms of p and q only, x and y also appear here, but to convert it into p and q only, we are to take capital X is equals to x plus y and capital Y is equals to x into y. The above approach cannot work here. We are to take capital X is equals to x plus y and capital Y is equals to xy. Now x and y, capital X and y are independent variable. So P is what? Del z upon del x. So we are to find derivative of z, partial derivative of z with respect to capital X small x, first we are to partially differentiate it with respect to capital X, and then we are to differentiate capital X with respect to small x. So del z upon del x is equals to del z upon del of capital X upon del x plus del z upon del capital Y into del capital Y upon del x, as del x upon del x is equals to 1, because capital X is equals to x plus y. When we differentiate this partially with respect to x, we get 1. If we differentiate it partially with respect to y, we also get 1. Now if we differentiate capital Y with respect to small x, we get a small y, and when we differentiate it with respect to small y, we get small x. So we will use this relation here. Then we get P is equals to del z upon del capital X plus del z upon del capital Y into y. Similarly, we get Q, which is del z upon del y, is equals to del z upon del capital X upon del y plus del z upon del capital Y upon del small y. So it becomes Q is equals to del z upon del x plus del z upon del y into x. Now putting the value of P and Q in given equation, here we will replace P and Q. We get this equation here: x by del z upon del y cancel out, del z upon del x cancel out. So remaining terms can be written as y minus x into y del z upon y del z upon del x minus x del z upon del x is equals to y del z upon del y minus x del z upon del y whole square. This is what del z upon del x, and this is del z upon del capital Y. So it becomes y minus x whole square cancel out in both sides. So it gives del z upon del x is equals to del z upon del y whole square, taking del z upon del x outside here and taking del z upon del y outside here. So we are left with y minus x whole square del z upon del x, y minus x whole square del z upon del y whole square. When we simplify it, we get del z upon del x is equals to del z upon del y whole square. This is P is equals to Q square. So let's take P is equals to A. We get Q square is equals to A, or Q is equals to root A, CB. And its solution is given by Z is equals to AX plus BY plus C. Capital X is X plus Y, capital Y is X into Y. So Z is equals to AX plus Y plus root AXY plus C. Here A and C are arbitrary constant. So these are some problem for solving. So that's all about first standard form when given equation in terms of P and Q only. Thank you.